and welcome to this discussion of doing calculations using a process or a technique called calorimetry. Calorimetry is a measure of heat, and while the SI unit for energy is joules, it was quite common in the past to use calories. And just to give you some perspective, 1 kilocalorie is equal to 1 food calorie. So they'll use a capital C for a food calorie because it's the same as a kilocalorie, and that equals 4.184 joules. Okay, so we're going to deal in joules primarily. And in this case, what we're typically looking at is heat transfer. And it's common to transfer that heat into a reservoir of water. And the reason is water actually has a fairly high heat capacity. That means you can add a lot of heat to water and not change its temperature very much. Remember, the bigger the heat capacity, the smaller the temperature change. Okay, now we're going to be doing a variety of processes. Sometimes it's dissolving a salt. Sometimes it's neutralizing an acid or base. But the key is that the heat lost by whatever process we're looking at is going to be equal in magnitude, but opposite in sign the heat gained by the water, or in some cases, instead of water, it's this bulk solution that is surrounding the process. Okay. Wow, that sounds really complicated. Well, you know what? It's use an MCAT and then use an MCAT again and maybe using another MCAT. So it's not quite as complicated as all these words sound. So let's take a look at an example of one. This is a common introductory laboratory calorimeter. Of course, to do food ones, you use what's called a bomb calorimeter. This is a constant volume process, and what you do is you combust your food with oxygen, and that combustion is going to transfer the heat to water, and we measure the heat change in water. But surprisingly good calorimeter are 2 styrofoam cups nestled together. So don't be surprised if you do this experiment in your lab, whether you're at college or high school, if you're going to nestle some styrofoam cups for this, because you really do get some pretty decent results. Now, what's going to happen in this case is we're going to take NaOH and we're going to dissolve it. So we're going to take the solid and we're going to take it and make it aqueous. Now, that point at which bonds are broken and bonds are formed is our system. In this case, the bulk solution would be our surroundings. So Q of my dissolving process is going to be equal in magnitude but opposite in sign of, I just call it bulk solution. I don't know why, to separate it from that point of bond breaking, bond forming. You know for sure that you're dealing with bonds with the solution because it says, assume that the heat capacity of the solution is the same as that of water. And the heat capacity of water is 4.184 joules per gram degrees Celsius. Okay? So what we're going, it's equal in magnitude, but this is important, equal in magnitude, opposite in sign. Okay? If the dissolving releases heat into the water, then that means that's an exothermic process. The water temperature will go up. If, on the other hand, the process pulls heat out of the water, that means the process is endothermic and it's sucking its energy out of the water, and the temperature of the water will go down. So let's see what happens here. I'm going to start with doing first Q of the solution. So my mass of my solution is going to be my mass of sodium hydroxide plus my mass of water. So I have 151.095. Once this has dissolved, it's part of that bulk solution. So that's my grams of my solution times the heat capacity of the solution, which we're assuming to be the same as water, times my temperature change, the final minus the initial. Now you notice that my solution temperature increased. So if my surroundings increase in temperature, that must have meant heat was released in this process, making this an exothermic process. And our math should bear that out. So Q of my solution is, when you do that algebra, is 1.15 times 10 to the third joules. Well, remember, my dissolving process, Q of dissolving, is equal in magnitude but opposite in sign, Q of my solution. And so this is minus 1.15 times 10 to the third joules. Okay? Now, sometimes you'll ask, that's for 1.095 grams. Sometimes you'll be asked, what is it on a per gram basis? Or if you already understand moles, on a per mole basis. And so I would simply divide it per gram of my sodium hydroxide. And I got minus 1.05 times 10 to the third joules per gram of NaOH. Okay, so hopefully that introduced you to calorimetry. If you just think of these mathematics as a step-by-step process, I think it will simplify the work and, more importantly, help you understand the concept a little bit better. Good luck with that. Take care.